Well, good morning. So now I can ask you a question. Now I'm asking you a question. Now I'm breaking the law by drinking, like many of you. So, this is just a wire, any wire, large, short, long, small. Doesn't have to be straight. It can be bent into a circle. A battery can be connected or inserted, and that will make a loop with electric current. So if you face it relative to you, electric current might travel clockwise or counterclockwise. There are no other options. Well, sometimes we may need to take a look at it aside. So in that case, you don't see electric current traveling in a circle. You could see it up or away from you, or imagine down or toward you. It's all in our ability to visualize things. And as we know, for a straight line, we can use the right-hand rule, but no one says we cannot use it for any type of line. We just grab it and watch it. The fingers will show the direction of the magnetic field, no matter how it's shaped. To be consistent, you can try several locations. You can grab it at the top of the loop, at the bottom of the loop, on the left and the right. And the right-hand rule should tell you the direction of the magnetic field, well, everywhere, including inside and outside. And this is too high even for me. So I'm going to imagine that I'm holding this. But that's wrong. Electric current should point in opposite direction. So this is how I should hold it. This piece of wire. Electric current, magnetic field. So if I look at them, now relative to me, those fields are clockwise, but of course I can always imagine that I do have magnetic field vector, so it will be right below this piece, will be pointing well toward you, up, in, down, everything according to the right-hand rule. It's all in our ability to visualize things. So down, left, up, that's electric current. And for magnetic field lines, kind of circles like this. And this symbol represents magnetic field vector, should point away from us. Well, technically, everywhere. Inside this loop, in the plane of the loop. And of course, there is an opposite situation when electric current travels counterclockwise. But we don't have to use this right-hand rule every time because, well, you can, but the physicists had invented another right-hand rule, also that number 3. Yeah. So this is how it works. If you have a loop with electric current, you use the same right hand with the same kind of orientation, but differently. Now, these fingers have to show the direction of electric current, and thumb will show the direction of magnetic field inside the loop. Well, technically, the only point we need is in the middle. So here, a magnetic field points into the screen, and here, magnetic field points out of the screen or out of the page if you look at it. So, and to calculate the strength at the center, because inside the loop, technically it changes, but at the center, the strength is, again, proportional to electric current and inversely proportional to radius. The difference between this equation and equation for a straight line is a pi, the number. Yeah, there is no pi here. That's it. Now we can solve a problem. Please read act, solve. We have two sources of magnetic field in this situation. One source is the long straight wire with electric current directed to the left. And second source is a circular loop with electric current traveling counterclockwise. That's how we call that direction. And each source generates its own magnetic field everywhere, including this point. This point is the middle point of the circle, but also this point is spaced away from the wire. We know, well, technically we know electric current because we could solve it, but we don't have to. This whole combination is a given number, and we know the distances. So the standard strategy for any problem-solving process is first embracing yourself, then reading, then viewing, then drawing. So right now, you should be drawing what? Well, each source is responsible for its own individual magnetic field. Two sources means two individual magnetic fields. You have to draw B1, B2, calculate B1, B2, and then add them up as vectors to get the net. So bye. I'll be back in 2 minutes and 20 seconds. Of course, you can talk to each other. I would encourage you actually to talk to each other. I'm back. I can't do nothing for so long time. You're thinking, that's what's wrong. You need to draw one arrow or a symbol which represents that arrow. That's not the picture related to, you have two notebooks, multitasking. So where's the arrow which represents magnetic field generated by the first current? That should be an arrow. Okay. For any standard arrow, we have 6 standard directions: left or right, up or down, into the screen or out of the screen. And for the straight wire, we can apply the right hand rule number 2, I guess, and for the loop, the right hand rule number 3. The most important fact from that we should take is, will magnetic field number 1 and number 2 parallel to each other, or will they be opposite to each other? That's the most important. So ideally, this is how every single problem should have been done, but that would take probably like 5 more semesters, time-wise. That's why some people have invented homework. So, I'm going to ask you a question about the direction of magnetic field at this point due to first wire. If you think that magnetic field points to the left, please raise your hand. To the right? No? Okay. Up? Down? Out of the screen? Correct. And for the magnetic field number 2, what do we say? Because electric current should travel counterclockwise. That should be our fingers, out of the screen as well. That's it. That's the most important part, because now we know what to do. Now we just have to plug in numbers, calculate each magnetic field. So B1. Well, first I just write it. And this whole combination, right? Just please check here. is equal to 10 to the negative fifth, and we need to divide it by the distance from a... Now, how do we measure a distance from a point to a straight line? Could have been many different lines drawn connecting a point and a wire. Actually, infinitely many. So when we say point P is 30 centimeters from the first wire, what does it really mean? The shortest, always, which is perpendicular. And the point 3 has to be converted into meters. And for, bless you, B2, we should write a slightly different equation. And technically, actually, it should be also marked, labeled R1, R2. So, what do we know about current? The current number 1 is twice of the current number 2, which means the current number 2 is a half of the current number 1. So, 1 half I1, 2 R2. Of course, I can calculate the numbers, but for me it's just easier to use that combination again, because I know this whole thing should be equal to 10 to the negative fifth, now times pi, and this should be the radius, 10 centimeters, 0.1. And now, as we said, here, B1 points out of the screen, and B2, just checking, also points out of the screen. Hence, B net is just B1 actually plus B2 in magnitudes. I think I have the answer. Well, actually, this number has been used yesterday. That's about 3.3 roughly times 10 to the negative fifth. Right? So if I multiply 10 and 10, 10 over 3 Tesla. And this number, I want to multiply by 10 again. That's going to be 10 to the negative fifth times 3.14, about 31.4 Tesla. So I'm just adding 31.4 plus 3.3, 34.7. On Weber sign probably should have been converted into, I don't know, nothing really. 347 micro Tesla times 10. Yes?
How did you get rid of the 1/2 before the current in the second equation?
I use this here because of this statement.
But when you calculated, you didn't use it.
I didn't use 1/2. Why have you been waiting so long? So, over 2. You can fix it. Well, that's an illustration. And now, the whole theory about a single loop is not so important. What's important is the next step. If you make a device which has a name, a coil or a solenoid, which looks like this, which made of many individual loops, each loop generates its own magnetic field. So if you have many loops like that, to calculate the total magnetic field, we just have to add them up, and that's the result. And this, well, we just multiplied by the total number of loops. And in this expression, the n is the total number of loops, and the L is the length of the solenoid. People usually use just little n as a density. And the magnetic field inside, as we saw, is practically uniform. That's what's good about it. But it's not very strong, unfortunately, because even if we have many loops, still, the coefficient 10 to the negative 7th makes magnetic field very weak, much actually weaker than electric field. It still there, it still affects the compass, but you cannot do anything very practical with this. It's not strong enough to lift the weight. That's why we use a core in every solenoid like this to amplify magnetic field. And this magnetic field now, due to this core, is about 1,000 times stronger than without core. Every material has certain magnetic properties, but well, some of those materials, like iron, can amplify magnetic field by a very large factor. We'll talk about it, the reason for that, but in general, it's because in iron, if we look inside, we can find many tiny magnets which point chaotically in all directions. An external magnetic field aligns them in the same direction, and that makes the whole magnetic field much stronger. So this is an expression which we can use to calculate the strength of the magnetic field inside the core of a solenoid. And this device, a solenoid with a core, also has a name, an electromagnet. So there's a permanent magnet, and this is electromagnet. Now we're going to talk about how magnetic field affects a loop. We know that magnetic field affects a wire. Remember? Well, let's see it once more time. Too many wires. Okay. What's this? So I'm giving you time to think about it and answer your question. And to answer this question, all you have to do is calculate net force. This is a square loop. It has 4 sides. Each side is represented by a straight wire. For each side, you can use the right hand to figure out the direction of the force acting from this magnetic field on the side number 1, on the side number 2, side number 3, side number 4, we know that there has to be force. That's not new. But now, we also want to know how would magnetic field affect a loop if it has any effect on it. Well, so you have to apply the right-hand rule for the force acting from magnetic field on the wire 4 times, and then add them up because that's what net force is. Number 1, what is the direction of a force acting from magnetic field on this side? Yes? So we have to use, yes, into the page, perfect, into the page. And the symbol for that is this. That's force number 1. Going to side number 2. What is the direction of the force acting from magnetic field on the side number 2? You're not answering question. What is the direction? It doesn't have a direction, it doesn't exist, because there is no force. It is 0. First of all, we cannot apply right-hand rule here, because for the right-hand rule, all 3 directions must be perpendicular. In this situation, electric current and magnetic field parallel, and if we calculate the force using the equation, it gives 0 because sine of 0 is 0. And of course now the magnetic force will be out of the screen. We don't really have to use the right-hand rule for that. We could, but we can say same magnetic field, but current switch to opposite direction, so the force has to switch to opposite to the previous direction, and it means out, and now 0 again. So we have 2 forces which must have the same magnitude, because for each force magnetic field is the same, length is the same, and electric current is the same. So net force acting on the whole loop will be equal to what? Into plus 0 plus out plus 0. What does it tell us? 0. There is no net force. And what's important is we can try a triangular loop, circular, trapezoidal, any, as long as it is placed inside a uniform magnetic field and we calculate accurately net force, it will be 0 again and again and again. A loop of any shape with any electric current, when it's placed in a uniform magnetic field, doesn't experience a force. But does it mean it experiences nothing? Well, oh, I need this. Let's see. So I have this loop, and I need to connect it to a battery. Oh, what's happening? It turns, it rotates. What physical variable is responsible for rotational motion? There is a name. It comes from PY105, but we still have to remember rotational dynamics. Yes, torque. Torque. So, if net force is 0, the net torque is not. How do we calculate torque? Well, we have to go back in time, remember the equation for torque of a force. Apply that equation twice, first time for that force, second time for this force. Then we have to add them up to calculate net torque. This can be done fairly easily. And, well, what actually helps very often is switching the point of view. This is what we see if we look at the loop like face to face. We don't see forces in that situation. Seeing forces helps. And for that, we have to switch our point of view. Let's imagine, it's an important skill. What would we see if we would be looking at the same loop from above? Well, first of all, we couldn't see the loop anymore. We would see a straight line, which represents the top side of this loop. We wouldn't see sides. But now we could see forces. So it's an important exercise relative to you if you're watching this loop. This vector for the force points into the screen. From a person, from an observer looking down, what should we draw? What vector here should we draw to represent the same force, but relative to a different point of view, relative to a different observer? So, yes? How do you know? What did you do? You have to do something. It's always in specific action. Proof is always actionable. So you can try mentally move yourself, or you can try to turn the loop. And that will be, relative to you, new perspective. So that's what you're doing. Your eye should look at this. How do you make it happen? Now your eye looks at this point. And this arrow, of course, now, relative to you, points up. And, of course, another arrow points down. And, of course, now, well, if this is 1/2 of this length, let's call it A, and this is 1/2 of the same length. To calculate torque, in this actually simple example, because forces are perpendicular to the line which connects axis of rotation and the line of action. So torque number 1 will have magnitude of force number 1 times the lever arm. And same for the torque number 2. That's A. But forces are equal, so torque number 1 and torque number 2 are equal to each other. And net torque, well, net torque will be actually clockwise in this situation, but the magnitude of net torque will be just 2 times magnitude of a single torque, and that will be equal to force times A. And how do we calculate the force? That's a magnetic force, Ampere's force. So it's I, L, B times A. In this situation, L represents the length of this side. Now, what do we have? Current, of course, magnetic field, of course. But what is product? L times A equal L times A, area. Exactly, area of this loop. So even we used a simple situation, a rectangular loop, the result stands for any loop. Shape doesn't matter, because any loop, any complicated loop, we can always break down in smaller portions which are perpendicular or parallel to magnetic field, etc., etc. So we can always represent it as some kind of a rectangular or trapezoidal. Yeah, that takes a while. That's what physics is about. Imagining small things, big things composed of. So, why do we call it the first extreme situation? Because that's the maximum value of a torque any loop can experience in a magnetic field. And why is it maximum? Because of this angle. If we start changing the orientation of the loop, this angle changes, and we know torque decreases. And what's happening eventually, of course, it should go to zero. That's the second extreme situation. So maximum torque, zero torque. And of course, anything in between. Now, we need to figure out a way to describe these situations. So that's what we do. We introduce, which means define, which means invent something new to describe the orientation of the loop relative to magnetic field. And that new thing has a name. The area vector. Where is my area vector? An area vector of a loop. What is it? According to a definition, which doesn't require understanding, it requires memorizing. The area vector of a loop is a vector which is perpendicular to the loop, and the length of it equals area of it. That's it. Well, we don't really need to know the length. We need to know the direction, perpendicular to the loop. How? Perpendicular to the loop, also perpendicular to the loop. In many cases, it doesn't really matter. We can just pick one. But historically, if we know the direction of electric current in the loop, if there is a current and we know its direction, in that case, normally people use the right hand to relate the direction of the current in the loop with the area vector. Again, doesn't have to be done all the time, but it helps. So for example, if this loop would have electric current traveling counterclockwise, we would use the right hand and we would say area vector points out of the plane of the loop or out of the screen. So now, here in this loop, area vector points into the screen or away from you. That's the area vector. But if we turn the loop, the area vector here points like this. So the area vector here, here, and magnetic field lines, as you can see, perpendicular to the area vector. This is always a case for the maximum torque acting on a loop. When magnetic field is perpendicular to the area vector, the torque has its maximum possible magnitude. Here, area vector is parallel. No angle, and the torque is zero. Well, so that's the area vector. With the right-hand rule. Now, the description of two extreme situations. And of course now, the general situation when the angle between magnetic field and the area vector is neither 0 nor 90. So this is the magnetic field. This is my area vector, the mutual orientation between magnetic field and area vector, that's only one thing that matters. Perpendicular, maximum torque, parallel or anti-parallel, no torque. What does it mean, no torque? It means that if I suspend it on a wire, nothing's going to happen. It will remain in equilibrium. What does it mean, maximum torque? It means if I suspend and I let it go, the torque will begin to spin it. So rotational motion begins. Well, technically, if torque is not zero, angular acceleration is not zero, so it starts rotating faster and faster and faster and faster. What's going to happen when torque is zero? Well, there's such property as inertia, so it will keep rotating. But now torque will try to spin it back, so it will slow down and it stops again. So this is an example of, well, oscillator. If we don't want to do oscillations, we want to, for example, make it spin constantly for a long period of time. That would have been a motor. What would we do? What would we have to do? Well, we would have to switch the direction of magnetic field or the direction of the current to the opposite. So it still would pick it up, keep it moving. Well, now you will never forget it. Some of you may have nightmares. So this is the general relationship which describes all possible situations. When theta is zero, there is no torque. Again, you have to remember, what is an official definition of this theta? That's the angle between magnetic field and the area vector of a loop. So that's what you need to see in your pictures, the area vector and magnetic field. If this is 90, sine of 90 is 1, torque reaches maximum value. And of course, if we have, well, not as big as this one, relatively small coil, each loop will experience this torque. So to calculate net torque acting on the solenoid, we would have to just multiply by the number of loops. Okay, so this is what I have mentioned already. If we have a loop in magnetic field, even if we hold it, even if there is no motion, the torque is not zero. But what is the direction of that torque? Well, we can imagine what would start happening to the loop if the loop would have been released. In that case, the area vector wants to become parallel, not feel torque anymore. So that would have been the direction of that rotational motion, which means this is how the torque is acting on this loop. Now, if you go back to PY105, we also had a right-hand rule for the direction of a torque acting on an object and a vector representing that torque. So here, if this loop would have been released, it would start moving counterclockwise. Counterclockwise motion says that torque acting on this loop can be represented by an arrow directed out of the screen. So you see how many right-hand rules we have. So this is how many right hands we need. Question. So we just have learned a rule. It doesn't require understanding. It requires enacting. So please enact. Here you see two arrows. The long arrow represents magnetic field. It's everywhere, but it's uniform. And the red arrow represents the area vector of a loop. We don't even need to see the loop itself. All we need is area vector. And now we have to make a statement about a vector which should represent the torque acting from this magnetic field on that invisible loop. We, of course, can make it visible. Yeah? We just can draw like a little circle which has to be perpendicular. Yeah? All right. I have noticed when I'm out, you start talking, so I'm out. But I'll be back. I can't hear you, so talk. This is a review of mathematics, basically, more than physics. You should have a copy of the picture. You cannot do it without a picture. Well, you're here, I can see it. So you need to draw two arrows. The question is how? Because the answer depends on the angle between two vectors. This is basically about the definition of the angle between two vectors. That's all. So from A to B. Did you do it the same way? Did you do it the same way? Anybody, everybody, everyone who did it the same way, please raise your hand or wave your hand. So you did it differently. You did it differently. You didn't wave your hand. How did you do it? If you did it differently, so anybody? You moved it. Well, this is not right. Question is what? Where's my? Okay. Here. Question is, what specifically is wrong with it? That violates the definition of an angle between two vectors. How do we measure an angle between two vectors? There is vector number 1. There is a vector number 2. How do we measure? There has to be a step, a procedure, an action which has to be done first. What is that step? Action. Now that's what adding a tail to a head is the rule which we use when we need to add two vectors. When we need to measure an angle between vectors, the rule is different. Tail to tail. They have to be drawn from the same point. So the action has to be drawing from the same point. So this is what I can do. Choose a point and redraw each vector. Of course, I could just move one vector to another one. And this doesn't require thinking. It requires knowledge of a definition. This is the angle between two vectors. Now, we can do some physics. Physics says, well, first of all, we have to imagine that probably there is like a loop like this. And the area vector is that vector which is perpendicular to that loop. And if that loop would have been released from rest, it would be moving how? By the shortest angle. So area vector always wants to be parallel to magnetic field. It doesn't want to feel any torque. So it wants to decrease the torque as fast as possible. So that would have been the direction of angular velocity. Yes?
What if it's 90 degrees? Then what is the shortest angle?
There is no shortest angle then.
It's not going to turn that way.
It will. But that would require an additional reasoning. What would happen if it would be 90, but would be 89.999 or 19.0007?
What if it's 90?
It doesn't want to become opposite. It wants to be parallel once. See? If this is your magnetic field, and let's say even not 90, well, could have been 90, could have been whatever it is. What is the shortest angle? It's not this, it's still longer because it wants to become parallel. It would have to go 130 degrees to become parallel. So it's going to still move like this.
So it's not.
Or like this.
So it doesn't want to be like anti-parallel, like the opposite. That doesn't work. It has to be in the same direction.
It wants to be parallel.
Also parallel.
No, that's anti-parallel. That's opposite. It doesn't want to be opposite. There's a word for that, conformity. So, and now this direction has a name, clockwise. Clockwise, and now if we use the right-hand rule, which relates the direction of actual or possible motion and the direction of a vector which represents that, it's out of the screen. No, I use the difference, clockwise into the screen, So this would have been a vector representing the torque acting on this loop. So if I used the standard Cartesian reference frame, x, y, z, torque relative to this reference frame would have been negative because it points opposite to z direction. Yes?
Sorry, can you repeat what the right hand was before?
I can try. Not sure. If it's gonna be clearer, because it's basically, again, a PY105, which you've taken a year ago, right? That's why I always recommend take them right after another. So if you have an object which can spin about any axis of rotation, and if you have a force, that's a force, or many other forces acting on it, we can always calculate the torque. Well, if we need it, if you need it, you should refresh. That's only one of possible expressions for the calculating torque. But also, if we describe the direction of it, first we'll look at how would this object move if nothing else would be acting. If nothing, and that is actually not related to physics, it's related to our everyday life experience. We have to imagine if that would have been nail and we would pull a string, how would it start move? Our common sense should tell us it would start moving, and that direction has a name, counterclockwise. And now we say if this object, if nothing else would act on it except this force, would start moving counterclockwise, the torque associated with this object has a name, counterclockwise, also has a value which is positive, also can be represented by a vector which points out of the screen. These are agreements, definitions. They have to be just internalized. And the opposite situation says that the torque responsible for the clockwise action can be represented by an arrow which points into the screen, and has to be treated as negative, which means it has a negative component relative to the axis. That's a definition. Yes?
The torque vector is, so the torque vector is not the one that's going counterclockwise. That's just the direction of motion. But the torque vector is going out of the screen.
The torque vector, well, first of all, it's not actually a vector, but we call it a vector. It's a special vector, different from velocity vector, but it is a representation. Vectors don't exist. Do you see any vectors? They only exist in our mind. It's a specific representation of certain phenomenon. And this phenomenon is an action, rotation, for example. And to represent that phenomenon, we use an arrow which points out of the screen or into the screen, which related to mathematical number, which we call a component, which could be positive or negative. Why is it important? For example, we used these definitions in lab when an object was in equilibrium. So net torque has to be equal to 0, which means all positive components plus all negative components should be equal to 0. And for that, we need to know how to figure out which component is positive, which component is negative, which torque is positive, which torque is negative. So it comes from that. And, well, let's solve a problem. So it's a flat rectangular coil with 25 loops in a uniform magnetic field, and initially the plane of the coil, which means the plane of each loop, is parallel to the direction of the field. We know the dimensions, we know electric current. Oh no, we need to calculate electric current based on the fact that the torque equals 5.4 newtons time a meter. That's a unit for torque. And then next question, if we turn the loop by 30 degrees, what will be the new value for the torque? So I'm going to give you a minute, just transfer numbers to your notebook. So we need to know how many loops, the strength of magnetic field. And this coil is not circular. This coil is rectangular. So each loop is a little rectangle. We know how long each side is. And the orientation is important. We know now that it means something very specific. We know that the magnitude of a torque acting on a loop for a magnetic field depends on their mutual orientation. Come on. That's a surface. Could have been Gaussian, could have been Maxwell, doesn't matter. This is the loop. That's the area vector. You look at magnetic field and area vector, you immediately should be able to say the torque equals what? 0, there is no torque. 0, there is no torque. Maximum torque. If we let it go, it starts to rotate in this direction. And in this direction, relative to u is clockwise. And relative to u, clockwise means that if you use right-hand rule, the torque associated with this action should point away from you, which should be negative. It's just probably easier to remember. Clockwise torque is negative, counterclockwise torque is positive, exactly like we used it in PY105. And in this situation, the information is not about the area vector, it's about the loop. Here, the loop is perpendicular to magnetic field. Torque equals what? 0. But now the loop is parallel to magnetic field. The loop, the plane of the loop is parallel, but area vector makes it perpendicular. The torque reaches maximum. So in this situation, we start from the maximum torque. And all we have to do is just write an equation. That's for single loop. That's for N. So 5.4 newtons time a meter should be equal to electric current, which we don't know, times magnetic field strength, which is 0.2, times the area. Well, area of a single loop will be equal to length times, oops, why did I do this? I don't know. I told you in PY105 that our brain always plays tricks on us. It's always a game between our brain and us. Times 0.15. The brain wins, by the way. Times 25. That's it. You just have to keep everything in international system of units. That's the question number 1 solved. We just need to calculate. over 0.2 times 0.12 times 0.15 times 25. I don't know what it is. You can finish it. Now, we make a turn 30 degrees. So the new torque will be equal to maximum torque times the sine of 30 degrees. For me, it's a coffee break. And for you, it is a sign of what? Something's wrong. Can you say what is wrong? No, you can't. You have no picture. You have no picture. You have no picture.
No, I have a picture.
Where? That's not a picture. No, you have no picture. No. Please raise your hand if you have a picture related to this problem. 1, 2, 3. Do you have a picture? So 3 students can solve this problem correctly. Do you want to solve this problem? Draw a picture.
I don't know.
What symbol do we use to represent the presence of magnetic field? B represents the strength of the magnetic field. The presence, the existence, is presented by what? A vector, an arrow, whatever you call it. So you have to draw an arrow to represent the existence of magnetic field. So draw an arrow. Draw it. What? Draw an arrow. That's all you need to do now. How do you pick a direction? Doesn't matter, it's up to you. The question is, in the mutual orientation between the loop and magnetic field. So you can pick the direction from magnetic field naturally to you. Natural to me means to the right. Now you need to draw, well, only one loop. We don't have to draw the whole 25 loops, just one. But that loop has to be initially parallel to magnetic field. So would even this parallel to magnetic field? No. My favorite word. So how do we draw it? Parallel to magnetic field? Well, if my direction is horizontal, parallel means to be, again, horizontal. Something like this. But of course, we need the area vector. How do we draw the area vector? Perpendicularly, up or down, doesn't matter. So you pick. And for me, a natural pick is up if I have a choice. Because I kind of always follow just x, y, z axes. That's it. That's the area vector. And now we have to make the loop turn by 30 degrees. So for the second question, the loop has to be turned by 30 degrees. From this orientation, it has to be turned by 30 degrees. Clockwise or counterclockwise? Do you know? Is it in the picture? Is it in the text? No, so you pick. Pick. That's my natural choice. So from this, and of course we can check what will happen if it would be moved counterclockwise. But we should expect it wouldn't matter, because there is no information. So from this, clockwise, we have to draw a new orientation of the same coil. So this is a picture before something had happened, and now we have to draw a new picture. When change happens, we always have to show both initial state and final state. So by 30 degrees, that means my area vector will be directed differently. This will be my new orientation of the loop, and 30 degrees was this angle, 30 degrees. Or this angle between the initial orientation of the area vector and the new orientation. This is 30 degrees. Now, oops, wrong. The equation which we have to use, well, for the magnitude of a torque is this. Now we have to use an official definition of this angle. What is an official definition of this angle? How should it be measured? Yes? Why? Because that's a definition, so we don't think about that. We just have to know it. This angle must be measured between magnetic field and area vector. So if you look at this picture now, what is the value of the angle between the magnetic field and the area vector? 60, it's not 30. That's it. That's why pictures matter. All right. Now all we have to do is just use this number times sine of 60. Probably someone already has it found for the maximum torque. Anybody? Oh, I did. Actually, maximum torque was known, 5.4. We don't even have to find it. We've been looking for electric current. But electric current is equal to whatever number here in amps. That's it. So this problem is much more about how to apply a definition correctly for the angle we are looking for or for using for, and that angle has to be measured always between the area vector and magnetic field. That's how it has to be measured according to a definition, because this is how the equation has been derived initially using this angle. And if you don't believe in that, you should go back to this slide, read the note number 1, and then use it. All right, so next exercise. Now I have 2 wires. Well, here, 2 wires which should, or maybe not, interact when electric current travels through those wires. To generate electric current, I have to use a power supply. So I'm going to switch to camera very soon, so you have to choose your answer. So plus electric current travels in this, then it travels here. Then I need to connect the wires together. Electric current travels through this wire, and now I have to close the circuit. No connection. Work. No current. So you should be entering your answer for what's going to happen, because you have all the means, all the information, everything you need to know in your notebooks. Okay. The bad connection hopefully has been fixed. Now you can compare your prediction with the actual experiment. Again, what's happening? Electric current travels through first wire, return, travels through the second wire, so in opposite directions. And now, how do we call this phenomenon? What do they do to each other? See again. How do we call it? Repulsion. Yep. Yeah, they repel each other. That's a repulsion. We had a very similar situation with two charges. If we had two negative charges, they repel each other. Now we have two wires with opposite currents, and the experiment tells us they repel each other. And by the way, can we make them attract each other? Well, of course, if they repel each other when they're opposite, that means if we change the direction of one current, they should start attracting each other. So what do I want to do? I want to make current travel here and then travel here again, and now should go back. See? Now they attract each other. So first of all, we can just memorize this rule. The parallel currents attract each other. See? That's what fingers tell them to do. They have fingers. We don't see them. Parallel currents attract each other. There is no rule for anti-parallels. We just have to remember that if they not parallel, they not attract. Not attraction, repel. So parallel currents attract each other, opposite currents repel each other. But of course, we must be able to figure out how is this happening. And we have time for that. Attraction or repulsion depends on the force acting on one wire from magnetic field generated by another wire. So that's all we need. So yes, we can. That's the rule. Now, what happens? This is a very useful exercise. So we have a wire, number one. Let's say with this electric current pointing up. How does it generate magnetic field? According to a right-hand rule, if we use the thumb, magnetic field lines are circular. On this side, they point out of the screen, and on this side, they point into the screen. So magnetic field will be directed into the screen. Now we are placing a wire number 2. And of course, the direction of a force acting on this wire for magnetic field depends on a second current. Well, we can choose, again, we started from opposite, yeah? So let's direct electric current down. Now we have to use the right-hand rule for the force acting from magnetic field on the wire. And that's kind of hard. So I have to turn the finger down, magnetic field, current, force acting on the second wire points to the right. But we could repeat the same reasoning backwards, or we can use the Newton's third law, which says when two objects interact, they exert forces which have same magnitude but opposite direction. That's it. Now, how we calculate this magnitude? Well, for example, F21 or F12 should be equal to what? Magnetic field strength, electric current number 2, times the length number 2. Magnetic field is generated by wire number 1, so that's strength of that. And how do we calculate magnetic field strength? Well, that's magnetic field strength of a straight wire times I2 times L2. What is R1? Well, technically it's a radius of that magnetic field line, but in this particular situation, this is also just a distance between two wires. And of course, magnitude of a force doesn't depend on the direction. So when currents are parallel, calculation is the same. The direction will be different. And of course, we have the slide. So this is a demonstration of a kind of difference in terminology between charges and wires. Here, like charges repel each other, but for wires, like currents, yeah, parallel currents, they attract each other. Well, and this is the equation which we can use to calculate the strength of that force. Of course, we only need to use that length where wire overlap, because they don't interact beyond this region. And no, I'm going to skip this, I'm going to skip this, I'm going to skip this, I'm going to skip. Let's do this. Don't answer the question. Let's, because right now we know in order to be, well, attracted or repelled, we have to use our imagination to see what's going to happen. So this wire is suspended on two conductive wires. And if nothing else is acting on it but tension and gravity, of course, these suspensions are vertical. But what if a third force starts acting on it? Not Democrats, not Republicans. The third force. It's being deflected. The nature of that force, of course, doesn't matter. In this situation, it's a magnetic attraction between a second wire and this wire. Now, all we have to do, and attraction means they have to be parallel. So All we have to do now is just draw a free body diagram. Let's draw a free body diagram. But this is not a diagrammic situation. It's a picture, it's a photograph. We need to see only forces. So we have to switch the point of view. We have to look at this bar or this wire straight at it. So we wouldn't see anything but one wire, which represents the first wire holding the first end of this bar. This is just the end of this rod, or wherever it is. Electric current travels at us, trying to focus in an eye. And this arrow represents the force of tension. This arrow represents the force of gravity. And because there is attraction, it has to be magnetic force directed to the left. But in equilibrium, net force must be equal to 0, which means, and we've done it many, many times already, this plus this plus this equals 0, which means if we draw a triangle formed by these forces, in this triangle, this angle should be measured from a vertical direction and one of the strings. And again, those strings are conductive, otherwise there wouldn't be current through the system. So we have to imagine, actually, there's a continuation. So look, like a couple of more wires, there's some battery here, because otherwise there wouldn't be electric current. Same here. Again, we have to imagine some wires, some battery, otherwise it wouldn't be electric current at all. But now we know what to do. That's mg, that's magnetic force. This is a right angle triangle. Magnetic force over mg will be equal to the tangent of that angle. And the rest is, I don't remember when I did it last time, but now I want to do it. Physics is done. Math begins. Thank you. All right.
For that equation, is the L referred to the length of the first eye or the second eye?
Where is it? Here.